So in this video we want to look at the vector space of functions that map real numbers to real numbers. So we're going to denote this set of functions as big F sub r, and we're going to let this set be the set of all functions f whose domain is all real numbers, and that maps real numbers to real numbers. So what we're saying is for our functions f, they have domain x running from negative infinity to infinity, and the outputs have to be real numbered outputs. And then we're going to define addition this way. F plus g of x is just the sum of the two functions. And because the function outputs are real numbers, this is just going to be a real number plus a real number for each value of x. And then we're going to denote scalar multiplication as just taking the function and multiplying it by the scalar. So an example here would be letting f of x equal, say, x plus x squared, and just letting g of x equal x. So using this definition, we would say f plus g of x equals f of x plus g of x. And this should have been defined for you when you took your pre-calculus course, so we're kind of just rehashing a little bit what was done there. So that's what f plus g of x would look like, and scalar times f of x just means take the scalar and multiply it by f of x, which just means take that scalar and multiply it by however you have defined your f of x to be. So the inputs have to be all real numbers, so we would be excluding things that look like 1 over x. So here we would get division by 0, so the domain would only run from negative infinity to 0, not including the 0 union 0 to infinity. So we're excluding guys like this from our conversation. And when we say that we have our functions f map real numbers to real numbers, so even though x can be any, x must be able to be every possible real number for inputs, the outputs can be a single real number. So for example, if we had h of x equal 5, it would meet this criteria because you can plug in any real number you want for x, and the output is still a real number 5. So the outputs don't have to be, the range doesn't have to be all real numbers or negative infinity to infinity. We want the domain to be all real numbers. The range just has to be a real number. So it turns out if we set this definition in place, if we describe the domain and range this way, and define addition and scalar multiplication this way, then f sub r happens to be a vector space, and we can show that it meets the 10 criteria that we laid out in our previous videos. We're going to go ahead and show that it meets these criteria, properties 1, 2, 3, 5, and 6, and then you'll show the other properties in the homework assignment. So the first two properties were just closure properties. So if we let f and g be elements of big F sub r, and we let c be some scalar, so some real number scalar, then if we look at f plus g of x equaling f of x plus g of x, what do we know from pre-calculus? Well, in pre-calculus what we learned was that if we have the sum of two functions and the domains of those two functions are all real numbers, then the result is a function whose domain is all real numbers. So taking the sum of two functions results in a new function h of x. But if the domain was all real numbers for f and the domain of g is all real numbers, then the domain of h of x is all real numbers. And that's from pre-calculus. And we know this about h. H is going to be a map that takes real number inputs and outputs a real number. Well, how do we know this? We know this because if f of x is a function that outputs a real number and g of x outputs a real number, we know that the sum of two real numbers is another real number. In other words, real numbers are closed under addition. So similarly, if we look at a function, let's use something other than h, so you say j of x equals a scalar multiple of f of x, then we know that if f of x has domain all real numbers, then just multiplying f of x by a scalar c gives us a function j whose domain is still all real numbers, and the outputs are going to be real number outputs, because a real number scalar times a real number is just going to be a real number. So similarly, j of x has domain r, all real numbers, and j is a map from the real numbers to the real numbers. And what this means is that the sum of the two functions and the scalar multiple of the function is closed under addition and scalar multiplication. So we can conclude from that f sub r is closed under addition. I'll try to write without my glasses on and see if that helps. And scalar multiplication. So if we try to show axiom 3 holds, axiom 3 is the commutative property. But what we want to note is so we'll say something like, note that because f and g map real numbers to real numbers, so the outputs are real numbers, then here's what we can say. We can say f plus g of x is just the sum of the two functions, f of x plus g of x. But because the functions output real numbers and real number addition is commutative, we know that we can reverse the order of this addition and still get the same real number output, but this is the same as doing g plus f of x. So the commutative property holds. So the commutative, I'm having a hard time writing today, commutative property, harder than usual, holds. So if we're trying to show 5, remember 5 is the existence of an additive identity. So this is pretty simple. You just say, now let, let's say big I for identity, big I of x equal 0. So we're going to let I of x be the function that for every real number you input, you output a 0. So it's just the constant function 0. Then what happens if you take f plus I of x? We know that this is, by the definition of addition, this is just f of x plus I of x. But I of x is 0 for all inputs, so f of x plus 0 is just f of x. And by a similar argument, we know that I plus f of x is also going to equal 0. So I of x is the additive identity. Additive identity exists. And then property 6 says, hey, prove that the additive inverses exist. So all we need to do is consider the function, let's call him h of x, that equals the opposite of f of x. Then if we have this, then we know that f plus h of x just equals f of x plus h of x, which equals f of x minus f of x, or plus the opposite of f of x, which equals 0, which is our additive identity function. And by a similar argument, if we do the addition in the other direction, the result is going to be the same. Sorry, I of x. So pretty straightforward, and then you get to do it for properties 4 and then 7 through 10 in homework 15.